Let's identify the reflection of point 0.03 on line L described as 2x minus 3y equal to 6. We know that in the previous video, we have the formula for the reflection of, let's say that's point x. So if x is equal to 0.3, the formula for its reflection along line L, this manner, is actually identified as that same x minus twice the inner product of x minus p in the unit normal vector times the unit normal vector. So again, x is identified, but in this case, p and the unit normal vector are not yet identified. So we'll be using specific concepts in determining those other details in order for us to determine the reflection of point 0.03 on the same line. But before that, let us illustrate that here so that we could also be guided with the rest of the predictions or analysis later on. If we have here the Cartesian plane and each grid is actually of 1, so you have here 1, 2, 3. So this is actually, we will find here 0, so it's actually in 0, x, and then y, which is equal to 3. This is actually 0, 3. This is actually where we can locate our x. X is at 0 and 3. Now, for our line, since we don't have points for that line, we are to determine the graph of the line first. So let me insert here some concepts. So to graph your line, which is 2x minus 3y is equal to 6, we may need 2 points, right? 2 points determine a line. So for our x-intercept, let y be equal to 0. So you have 2x minus 3 times 0 is equal to 6. 2x is equal to 6. So x is actually 3. Our x-intercept is at 0. Sorry, that's 3 and 0. For our y-intercept, we actually include this process because we just want this topic to be understood even with the use rather of our illustration. So we have here let x be equal to 0. So 2 times 0, sorry for that, 2 times 0 minus 3, y is equal to 6. That's 3y is, negative, is equal to 6. So y is negative 2. So the y-intercept is at 0 and negative 2. We're going to plot that here. So 3, 0, I'm talking about this, and 0 and negative 2. So this is our point, 3, 0. This is actually 0, negative 2. So if we're going to connect it with a certain line, hopefully I could actually connect them in just one attempt. Let's assume that my graph is okay. And if we're just going to add arrowheads, okay, arrowheads. So that is actually our line. So the reflection along this line is actually located somewhere in the fourth quadrant. Because if we talk about the reflection of x along this line, it will be somewhere here. Again, the reflection would have the same distance, shortest distance. So if we have here the shortest distance to that, will be reflected somewhere here. So I'm just assuming it will be somewhere here. We don't know that value yet, but we are actually guided. It's a fourth quadrant. We are expecting positive value for your x, for your abscissa, and negative for your ordinate. So that's our guide. So by the way, again, this is our foot of the perpendicularity, but we will no longer solve for that. We're just going to automatically apply the formula. So since we are guided already that our reflection somewhere here is on the fourth quadrant, let's talk about the quantity or the criteria, or what do you call this one, the details needed to identify the reflection of x along the line L. Again, our x is already okay. Now let's talk about p. Now on our p, we're talking about a point on the line, so you can use either x or y-intercept to that. That's already okay because the x-intercept and y-intercepts are actually the point on the same line. Now let's talk about the unit normal vector. The unit normal vector is actually the normal vector with magnitude or length of 1. So let's talk about that first. We can actually take that from this equation. Our equation is actually identified as 2x minus 3y is equal to 6. This is actually our A. That's actually our B. We don't need C for that because A and B are given. Our normal vector is actually composed with A and B. So our normal vector is 2 and negative 3. Take note, it should be 2 and negative 3. By the way, other references would like to accept parenthesis. We just simply using this one because we would like it to be differentiated by any point, but nevertheless this is also a vector itself. But the formula allows us to use the unit normal vector, not the normal vector itself. So we still need to get the unit normal vector. In the previous examples, especially in the discussions of foot or perpendicular, we have this formula, your normal vector over the length of the normal vector. The length of the normal vector is actually equal to the square root of the squares of the sum of the squares of the components. 2 squared plus negative 3 squared. You will have here 4 plus 9. So you have square root of 13. This is the length of your vector n. So using this and these components, the unit normal vector is identified as you have 2 and negative 3 over square root of 13, or you could also have 2 over square root of 13 and negative 3 over square root of 13. Now we have our unit normal vector, already have our x earlier, and let me choose the x-intercept for our p. It's now time for us to determine the reflection of our point x along line L with the formula x minus twice the inner product of x minus p and the unit normal vector times the unit normal vector. Okay, so you have here your x is actually again 0, 3, the reflection of 0, 3 along the line L. So you have here 0, 3 minus 2 times the inner product of your 0, 3 minus, let me use the x intercept. You could even use y-intercept if you would like to for easier process. I believe it would be easier because you will have here 0 and negative 2, right? So you'll be having zeros. So allow me to shift my process instead of using the x-intercept. By the way, this is also one of the techniques that you may use. I'll be using the y-intercept because when I combine that, the first components would be 0. It's easier for me to really combine that with our unit normal vector, which is expressed as 2 over square root of 13, negative 3 over square root of 13. Inner product of that would still be multiplied with 2 over square root of 13 and negative 3 over square root of 13. Okay? So I'm using the y-intercept for this matter. So I have here 0, 3 minus twice. So the result for this is actually, again, 0 minus 0, it's easy. 0 and then 5. That's 3 minus negative 2. That's our point. But it will be under the inner product of 2 over square root of 13 and then negative 3 over square root of 13. Why is it that I chose the possibility of coming up with 0? Because if we talk about the inner product, we'll be multiplying the components, and 0 times this, that will be 0. It's easier for us to really have that later. Don't forget that we still have here these notations. So continue. Again, please be guided that our reflection is on the fourth quadrant. So you have here 0 and 3. So this is minus 2 times, again, multiplying the first components. 0 times 2 square root of 3. That's actually 0. This one here. So it's actually 0 plus 5 times this. So that's negative 15. So plus negative 15 over square root of 13. By the way, similar in solving for the foot, there's no need for us to rationalize that because later on we will be dealing with also results no longer having radical expressions in the denominator. You have here 2 over square root of 13, negative 3 over square root of 13. Hopefully the spaces are okay. 0 and 3. So this actually 2 times, this is of course negative, right? So negative 2 times negative 15. So that's positive 30 over square root of 13 times 2 over square root of 13 and negative 3 over square root of 13. This is now scalar multiplication. As you can see on our denominators, when we multiply radical expressions, then we will have rational answers now, because square root of 13 times square root of 13 is just 13. This is now equal to 0 and 3 still, plus, that's 30 times 2 is 60 over 13. Let's not simplify them in the meantime. And 30 times negative 3 is negative 90 over square root of 13. Okay, hopefully it's okay and it's correct. So we add them for final result. You have 60 over square root of 13. Sorry, there should be no square root anymore. So that's 60 over 13. And then you will have actually, what is 3 minus 90 over 13? You may use calculators if you would like to, which would give us a result which is actually equal to, again, the x is 60 over 13, and you have your negative 51 over 13. This is now the reflection, okay, of your x along line L. And as you can see, the x is positive, the y is negative. Clearly, it's actually located on the fourth quadrant. Now, for better illustration, let me copy this, and let's see by our presumed graph earlier. Let's find out if the result would be closer to that. So 60 divided by 13 is actually 4 point something. So our point must be in 4. That's positive 4 point something, 0.46, so somewhere here, 0.6. Okay, and then for negative 51 divided by 13 is actually negative 3.9. So 1, 2, 3, almost 4. So basically our point is actually just this one here. This is our point here. This was our reflection. So our assumption earlier was quite far, but nevertheless, that's why we are doing this, to illustrate really its location. So our x prime is somewhere here. So we can see that it's really on the fourth quadrant, and it usually shows a reflection of point x along line L. So again, we're using this formula, and by the way, before that, we were able to illustrate that in the Cartesian plane just for us to be able to see a picture, so we will be guided probably on what are the possible results. Because if in case our answers here, just in case, are actually yielded negative, that's actually in the third quadrant. Basically, we know already that it's incorrect because it should be in the fourth quadrant. So we can actually use that as part of our review, that or in the review of our answers, that our answer is actually incorrect if we get incorrect signs. Okay, that's for this, and we'll have more examples. Thank you very much for watching.